ben. Okay, so welcome everybody. So thank you. We're going to present now our platform at Imperial College. As I said before, we've got quite heterogeneous platforms. Some of them are extremely similar to some of the other robotic platforms, but some of them are really more specific and not directly platforms. So this came to the genesis of TERRINet. I think that there is both robots as platforms and platforms for robotics. Okay, so we're going to talk about three different topics, one after the other. And I'm going to start with a general introduction of Imperial. So for the people who don't know, Imperial College is located mostly in the center of London, in South Kensington, and that's where we've got our main campus. So it's really in the historical part of London, extremely close of Buckingham Palace, really just next to the Royal Albert Hall. We also have some campus directly into hospital and hospital in collaboration directly with those hospitals. So this is also really good implantation of the center, not only with any engineer, but also with directly collaboration with doctors. Today we're mostly going to focus on the Hamlin Center because we have all the three from the Hamlin Center. But we also want to replace some of the platforms that we originally proposed in Imperial with some other platform from other departments of Imperial. So for now, I'm just going to present the platform from Hamlin Center. So Hamlin Center has been here for about 10 years now, and it's meant for development of engineering technology for medical applications. So one of the big focus is medical robotics, but we also have some other interest in assisted vision and just generally development of technology for medical applications. So more or less what I was saying, what we've got in the Hamlin Center is mostly a focus on research and teaching, but also those technology platforms, and that's what we're going to present today. Those technology platforms first are for the research and development of the Hamlin Center. They're also, and there is a huge emphasis on translation of this technology. So we don't only develop technology for technology, but we also develop technology to be applied directly in the operation theaters and to be used directly by surgeons. And finally, there is technology platforms that can be used by researchers from Imperial College London, by other researchers into different networks in the UK, and clinicians, of course, as I was saying, and finally for European research, and that's what I'm presenting today. So we are included in different programs, but TERRINet is the big one, and we just also propose some platform on DIH Hero, which is another general platform more targeting selling services toward industry, but from European research. Okay, so we're gonna go through the different platform and give you some example. We're gonna go fairly fast and be quite descriptive, and maybe stop a little bit more on some specific example. So Denise and Antoine gonna present more in depth the research because researchers like to present the research. Okay, so the first platform that I'm going to present is our motion capture and virtual reality platform. We're using it for a lot of applications, going from healthcare monitoring, patient monitoring, a lot of preoperative and postoperative monitoring, gait analysis, and all of this can be integrated in virtual reality environments. A lot of extremely heteroclite equipment that allow for various simulation of scenarios such as sport practice, movement in an hospital environment, medical bed assistance, assistant robot, and so on. It's equipped with a very complete motion capture system, so 10 Vicon system, one view camera, so with a higher frequency, and it's coupled with all the other systems that we have in the system. So EMG data tracker, and it can be coupled also with some of the. It's coupled a lot with a lot of equipment that we've got to simulate sports like treadmills and other simulation. So electrography system, same thing for precise monitoring of limb movements. Huge research areas that we are doing. I think I put an example after. Yes, no, anyway. Huge research. Huge research areas that we are doing is trying to minimize the number of sensors that are used for specific application. Indeed, when you want to have an information, for example, a patient who is at home, and you want to know if they've got problems, if they've got trouble, or what they are doing, trying to monitor them and so on, you do not want to have them equipped with a sensor or in every single joint, and you want to have minimum invasive sensors. So we work on this. This example, for example, was try to compare our different system and what we can get from a single image analysis compared to what we can get with the full Vicon systems. And it was meant to detect various walk impairments that you can have and problem directly on the lower limbs and how they affect the gait movement. All of this is also coupled with brain-computer interface. So we do quite a lot of rehabilitation, and we try to, again, have different way to control them and direct feedback with brainwave recording. So we've got some EEG systems, some wireless channel EEG system, both wet and dry, and some other integrated NRS EEG system. If you got more questions on this, please do not ask me. I really do not really know how it works. And as I was saying, all of this integrated with various equipment of virtual reality and augmented reality. So with Oculus Rift, and we just recently get this Catwalk Mini for movement, like simulation of movement and playing video game at night. Okay, and finally an example on this. So for the movement recognitions, we are working on some exoskeletons and improvement of those exoskeletons. A few research on control of this exoskeleton through brainwave directly. And this is just another paper where we explain this type of reducing of the number of sensors and how you can get full information from minimally invasive sensors. Okay, so I jump directly to another completely different topic and another completely different platform, which is our fast medical robotic platforms. So it's I'm going to show you here. What I'm going to show you here is not only a large collection of 3D printer, or at least a collection of large 3D printer, like industrial scale of 3D printers, but also all environment will allow you to design, assemble, certify, and test your prototypes. And Danny's going to finish this part with an example of his platform that he developed with his colleague in these platforms. So, and this is quite specific for medical robotics because medical robotics need, especially if you want to do human testing, a lot of characterization that you do not have to do to another robot who can fail, because those robots cannot fail, and those robots need to be assembled with extremely specific hygiene protocols, and we've got all these possibilities in our lab. So quickly now on the description. We've got both FDM and polyjet printers, so we can make, one is used for extremely large structural parts and with a build size of maybe 1 meter by 50 centimeter by something like 1 meter or so. So quite a high volume of pieces for large robotic casing. Also biocompatible material can be used for prosthesis test and so on. And other like multi-jet printers that can print different type of polymers at the same time, and going from flexible to transparent, and a lot of variation in between. And that you use a lot for like soft robotic and so on, wearables. Finally, we also have for the fabrication part, a lot of micro machining capabilities who allow us, and I didn't put it here, and metal 3D printer who really allow us to fabricate not only the main part, but also a lot of the small mechanical components. Finally, as I was saying, we've got all the assemblies facility with ISO certification that is working on then, and medical usage grade, so it's need to be done in a specific clean room environment, and specific sterilization in between usage before bringing anything anywhere close to a human, and for some of the legislation, sorry, even bringing to a cadaver. Finally, we've got a lot of facilities for the inspection and certification of those things. So it goes from micro-CT, so for checking the structural defect, for example, of the 3D printed pieces, automated mechanical tested. They also inspect the one on the top bottom right, which is a large-scale multi-sensor platforms. And we get one of the projects accepted for the call 2 is exactly what we are intended to. Somebody with precision robotic platforms, and they've got problem on the precision of the platform, and they want to understand why the simulation and the real robots have a difference, and they want to be able to characterize exactly precisely and to see where is the difference between the CAD model and the fabricated parts. Flying probe testers and large-scale electrical testing. And I'm going to leave Kundrat to explain to you one example and going down on the nanoscale after. Right after this. Good? Good.
So my name is Dennis Kundrat, and I'm also a researcher at the Hamlin Center. And I'm complementing this section with a use case of our in-house rapid prototyping facilities, just to give you an idea how it can be used and why is it quite useful, for instance, in medical robotics. So I'm in the team of endovascular robotics, and we developed this master-slave system, which was also initially driven by some knowledge from Twente University. And we have the master-slave setup. I don't want to go into details, but I also want to highlight where we used which printer for complementing or completing the design. So the master device is a haptic device, haptic master device, which can render forces back to the user and more or less mimics the motion that you have in conventional endovascular interventions. So for all of those who are not familiar with the endovascular intervention, it's usually based on catheter and guide wire interaction, which is inserted to the vascular structure. So usually you have translation and rotation, and this device mimics a linear motion and a rotary motion. And you can render via two motors torques and forces back to the user. So the entire device is built more or less based on our in-house rapid prototyping systems. For larger structural parts, as Florent already mentioned, we used the FDM printer, and for all parts that needed high precision, we used the polyjet devices. The remaining parts are off-the-shelf components. And then we go further to the most interesting part, because we propose to have an MR-safe system, and MR-safe systems should avoid any ferromagnetic materials. So the entire device is driven by air and is manufactured more or less from plastics. And why is it important to mention that this is also done by rapid prototyping? Because we are running right now some animal trials. So we have reached quite a high technology level already, and we are running some animal trials, and we have to reproduce the system within a few hours, because the sequence is quite, there's not a lot of time to reproduce the system. And I just put here the hours that I needed for reproduction of the system, which is composed of 4 linear motors that are inspired by the Twente design and that we have advanced right now. And then we have 2 rotary motors, we have the base, and we have multiple grippers that more or less enable manipulation of catheters and guide wires. And for the entire system, to rebuild the entire system, we needed like approximately 10 hours. And just a quick video how it looks like. So it's not only a mock-up. Oh, it's quite slow. Okay. So we can drive catheters and guide wires, and that's exactly what we are doing in the animal trial right now. So you can see all the parts are printed apart from these guide rails here, and then we can more or less manipulate the entire guide wire and catheter system based on rapid prototyping parts. Now I'm coming to some more another platform that we also propose for the TERRINet network, which are available in our labs. So just an overview, we have the Da Vinci system, we have the Raven robot, we have KUKA robots, and we have like a surgical surgical scenario that we can, but I will add some details further on. So let me start with the Da Vinci Research Kit. We already heard some facts about the system this morning. So usually it's a first generation Da Vinci system that has been transferred into an open source environment. So you have 2 instruments arms, 6 degrees of freedom each, plus 1 DOF grasper, 1 camera arm, that's this one. You have a dual master console. I will have some pictures on the next slide. You have a stereo laparoscope attached here. And what makes the Da Vinci Research Kit quite promising in terms of research, as we heard this morning already, it's more or less open access to the control layers. So we have access to low-level FPGAs, the amplifier system. But for most of us, it's more interesting to have high-level access, which is more or less based on the non-real-time loops and usually uses, at least in our lab, Ubuntu 16.4. And we also use the ROS interface. I have some details further on. Just a quick look at the master console. So we have the master input device here, and we have some more foot pedals that can be used for camera or catheterization tools. And usually, so that's how we use the system in our lab at the moment. So we don't use a lot of in-house developed software. We are more or less using the basic software provided by the Johns Hopkins University. And this also applies to the documentation. So first of all, the DVRK user guide or manual should be considered. The Johns Hopkins GitHub also provides a lot of inside information. And there are also some publications available on the DVRK software architecture. Predominantly, all this software on details of the architecture of the DVRK is published by the Johns Hopkins University. So if we have applicants that would like to use the system, we at least demand a basic knowledge of robot kinematics. I would say intermediate C++ or Python knowledge is favorable, because otherwise it's very hard even to get started with the ROS environment. So I would say an intermediate level is quite sufficient. And then it depends on the task that applicants would like to conduct at our institution. So for knowledge of further libraries from OpenCV to Eigen is demanded. So the initial training should be 1 or 2 days with trained staff. So that means in close collaboration, the initial features will be explored. But throughout the experiments, we will have at least 1 PhD on standby to support. And it's not only feasible to test algorithms, also new instrumentation can be targeted. So that means the instruments, let's see, 1 slide back. So we have the standard Da Vinci instruments here. These instruments can be, for instance, replaced with a customized bespoke instruments and then attached to the system. So if someone would like to test his hardware implementation, we are also open to test a new instrument with our device. So maybe that needs less programming knowledge. So our second platform, which is, or some examples that we conducted with the system, we did less on hardware design. We used it more for data acquisition or validation of other methods. So this is a quite recent paper that used the data acquisition with the system for an adaptive motion scaling sequence, or this is another approach where the Da Vinci, the DVRK was used for 3D pose estimation of surgical tools. Another system which is open source and more intended as a research system is the Raven 2 system. So the kinematics of the instrument and the arms are quite comparable to the DVRK, but it's just a different approach because it's more compact. We have also a dual haptic master interface here that's implemented with 2 Phantom Omnis. And it also provides an open access to the control layers. So that means real-time and non-real-time layers. It uses open source soft and hardware and also has, again, a ROS interface. Again, more or less similar to the Da Vinci system. Applications can be prototyping of algorithms. That's the first part. Or even testing new instrumentation, more or less analogously to the DVRK. So the basic software that is used is the available via the GitHub from the University of Washington Biorobotics Lab. That's the software that we run. So we don't have a lot of customized modules at the moment, only very specifically developed for the specific publications, but it's not like a generic one at the moment. The UV also provides a very good YouTube tutorial series, which can be, could be completed prior to any experiments. And there's also a very good Raven user guide and Doxygen guide available. So more or less similar, a basic understanding of robots kinematics is demanded, and an intermediate C++ and Python level should be available. So training, 1 or 2 days with trained staff, and then we have staff or PhD students on standby for any further help with the system. Some basic or just a quick overview of research that has been done with the Raven robot. Here, the bimanual task was more or less improved by incorporating learning from demonstration. And then we had another setup here, which was a probe tissue contact management implemented on the Raven robot for endomicroscopic scanning. So in both cases, the robot was more or less used like an instrument, and then different layers of software were augmented to improve the task or to improve the quality of the probe while imaging the tissue. So we also provide 2 KUKA robots. So I think most of you are familiar with the KUKA robots. 7-DOF system, redundancy. We have the 7 and 14 kilo payload systems. Force torque sensing, various research interfaces, FRI or the Sunrise interface are available, impedance control, gravity compensation, and also we have some media and data interfaces for customized end effectors. It depends on the demands. So the fast research interface, which is like a more or less historic interface, can still be used, or we can, for instance, provide the Sunrise or like a ROS stack that like builds up on the Sunrise interface. Documentation, the IVA or Sunrise user guides are provided, and then it depends on the specific implementation. The interface guys should be, let's say we use the Indigo, ROS Indigo stack, should be taken into consideration. Again, robot kinematics should be at least fundamentally understood, and intermediate C++ and Python skills should be available to get started quite quickly and not to waste a lot of time on the very basic things. We will have again 1-2 days with the trained staff, also due to safety reasons, and then we will have trained staff, usually I think supervising the experiments, because if you command the robot, it's more favorable if trained staff is around and might make sure that the system is used properly. So some examples of the robot: we implemented a bimanual stand graft sewing. So the robots were equipped with a specialized customized end effector for sewing stand grafts for endovascular surgery. Or another project was a gaze control of a laser manipulator. Finally, we also provide this environment, which can be seen like in terms of translational approaches that we favor at the Hamlin Center. So we would like to bridge the link between research lab and the clinical environment. And as Florent initially also mentioned, this this lab more or less provides consumables, it provides phantoms, it provides an OR table or further instrumentation, some screens, just to mimic the first step into the clinical environment. So if users would like to set up their customized devices, we can also provide this environment just to test it with a simple OR table, or if specific phantoms are required, we can provide a set of phantoms for specific tasks. So this is like a very multifunctional environment. And now I might hand over to my colleague, Antoine.
So hello everyone, I'm Antoine Barbot, and I'm also working in Imperial College, and on robotic, but on a much more smaller scale. So we are investigate how we can actuate it and also design sensors to have like basic feedback loop at micro scale. So because we have many different tools to allow this. So they are a bit both wrapped up in micro and nano robotic platform that I will present now. A few of this platform, and also a few of the work that have been done with this platform. So the first one is we've got SEM, which is a scanning electron microscope. So it's microscopes that work under vacuum with electrons, so we have a really high resolution to make it simple. And because it's in vacuum, it's really handy to have some micro manipulator inside. So we have this microscope. It's also equipped with a focus ion beam, so that can do machining at really small scale. And the manipulator can be moved either manually, which is what's done in this work, where we're just characterizing a small bistable mechanism, but also my colleague is attaching some spring part, which is a shape memory alloy. So attaching it and using this FIB, so focus ion beam technique, which can mill but also do like small soldering. So it's possible to have this platform. Everything can be controlled manually, of course. So it can be, in this case, useful for characterization, but also everything can be automated. So both the micro manipulator, which have nanometer resolution, have a C library, and also the SEM and FIB have the SEM library. So I would say if you already know SEM technology, the training can be quite fast, especially for manual control. Then if there is a project on automation, it will necessitate a bit more training, because it's an expensive equipment and there is no much safety on the movement you can do. So just need to be cautious. The next one is the nanoscribe, which is a 2-photon lithography, and so basically it's like a 3D printer but with a micron size resolution. And so it's possible to use it, and I put the workflow on the side. So it's really easy to be trained on this. It's a quite intuitive machine. As long as you can provide some CAD design, and you export in STL, which is kind of classical for a 3D printer, then there is a software just to generate the path, and we can provide some help to optimize the parameter here. And after, the machine is kind of straightforward to use, and for basic use in one afternoon, we can train people to use it. So how does it work? It's a microscope you see here, and if this is a zoom on the interesting part, so there is a laser that is shine onto the resist, and it's solidify at a precise location. So it's quite a common technique for 3D printing, but here the laser is a femtosecond laser, and so there is this two-photon effect happening in a voxel, which is really small. Yeah, also we have, and it's what I will show afterward of example of my work, but we have a method that was developed to print off the top of fiber. So that is this example where we put a fiber here and then we can have the structure in the fiber, whereas in normal case it's on a glass slide. So we use this, so this is not an optical fiber, but it's a capillary, and so we use it, for example, to build this this mechanism at the tip of a capillary. So it's just a pneumatic piston, and which using after we have another process to add a liquid drop here to make the sealing, the gas, I mean the sealing of the piston, so it can be actuated. And the cool part after it's we can do a small gripper, and if I manage to launch the video, so I don't know if it's launching or not. QuickTime not available. Okay. So well, basically, sorry for this, but this is like it's we're looking to have application for taking biopsy and so on with really small tools. So this is just an example where we manipulate, we pick a bead, and it's like this. When you go to a fun fair, you know, you have this game with a gripper and a lot of toys. So it's the same difficulty. So probably we'll organize also a game based on this. The other example is to do microfluidic at the tip of capillary. So it's also really useful for drug delivery or drug sampling. And in this case, thanks to this platform, we can print a junction between these two capillaries. And so we have this shape with, so it's a U junction with a lot of holes. And this allows to play with droplets, and basically the holes are small enough so the gas cannot pass through, because it's need to deform the surface tension quite a lot. So the gas cannot pass through, but when the liquid arrives, if it's miscible, there's no problem to make the junction and it's eject. Or if we have different pressure, it's sampling. So here you can see an example, and as I say, we use this today to develop like drug delivery and sampling, and have no much hope for this video, but maybe it will work. Oh yeah, so this is like a high-speed video, and hopefully it will work, and it doesn't work. Oh yeah, it's really slow. So you can see the liquid arriving and then being expelled. Well, we got few frames, so get expelled in the environment. So to move on, another platform we have, it's a mobile microrobots that are actuated by a small piezo resonator, and by tuning the vibrations, they can be moved. Also with a nanometer, well, let's say 10 of nanometer, 100 of nanometer, depending on the environment, but quite good resolution. But there is no, like, the feedback need to be optical, and so it's not the microscope we are using. I just took this their picture from their website, but we have another microscope that allow a much more working distance. So those tiny robots can be actuated, and then the optical feedback can be assured with the microscope. So they both have 4 degrees of freedom, which is the translation, 1 rotation like this, and the small arm also have 1 degree of freedom. And we also have the platform to equip them with 4 sensors. So of course, micro force sensor. So we have, I mean, well, it's a hub, but it's probably down to 5 piconewton resolution. So to make like really precise force characterization is quite useful. And so the training is to be used manually It's just one day if it's to characterize a system, but then there is also a C library. There's also a C library to control the microscope, and OpenCV can be placed in between to really close the loop. So in this case, it will require maybe more than a day of training, and we can arrange for to identify the need of the user. So that's just an example of one force characterization. So again, we use this to characterize the force of the piston, and it was quite tricky to align the two. So we use both position robot just to put the piston in front of the force sensor, and then just measuring a square wave. And finally, this last one is really an experimental platform, but it's also open for TERRINet application. It's a micro robots alignment platform for wet transfer, and so to pattern flexible electronic. So we developed and this is made to pattern on fiber or on micro catheter. So we developed this platform, so we could like place flexible electronics. So for now we are mostly doing really simple gold connection, but we can place it on a fiber with a really good precision, and we are working toward printing them, transferring them on more complex 3D geometry. So it's the same for this. It's really user-friendly, so it can be used quite easily if someone can, if the user provides the flexible electronic you want to pattern. Then, if you don't have any flexible electronic, then we need to discuss to build it in-house, but it's still possible. And so quickly, how this thing works is these two floating robots are just polymer with some iron powder inside, which is aligned in a specific direction to store a preference direction of magnetization. So in this way, they have a different preference of magnetization. So when they are placed under the magnets, they sit in two different equilibria. And so by playing with the magnet translation, but also altitude, we can have a gripping effect. So we can pick and place the floating device and then transfer it. And I guess there was a video, but I'm afraid it won't work. And anyway, maybe we are super late. Well, let's pass to the last platform. I promise it's the last. We have optical tweezer, so which allow a manipulation of micro objects. So it's also available for the network, and it can be automatized. There is a lab view interface for really quick, I would say, open loop actuation, and then we are working to develop more closed loop. So by placing visual tracking in the between, so it's also possible. But in this case, applicants should need to have a good knowledge in C and probably OpenCV. We also offer this tiny magnetic device, which allow to generate a 10 millitesla magnetic field in any direction and to rotate it and for micro robot actuation or any need for a magnetic field. And this is just this require C++ knowledge, but it's it's a fairly simple thing. And the two can be combined. That's the example we show here, where we can do hybrid optical manipulation and magnetic stimulation. Yep, and that maybe Florent wanted to, it's just Florent wanted to advertise for a conference, the conference we organize on medical robotic, which is all surgery and beyond, which is really optimistic. Yeah, so if you're available, please come.